Hey everyone, and welcome to The Explainer. Today, we're jumping straight into something that is literally a game changer for data storage. If you work with massive spatial files, things like LiDAR scanning, immersive VR, or super high-res medical imaging, you already know the massive headache of trying to compress those files without completely ruining them. Well, today we are unpacking a protocol called SHD CCP. Specifically, we're looking at Concept Alpha version 1.4.2. That stands for Lossless Spatial Compression via Symbolic High-Dimensional Context. And yeah, I know it's a mouthful, but it absolutely shatters how we currently handle 3D data. Let's get right into it.
Okay, let's dive into this. Here is a quick roadmap of what we're covering. We'll start with Section 1, the 3D compression problem, basically looking at why our current codecs are totally failing us. Then, in Section 2, we'll explore the core seed hypothesis. Section 3 gets into the math and block classification running under the hood. And finally, Section 4 is the ultimate performance comparison. All right, Section 1, the 3D compression problem, and specifically our baseline failures. To really get why SHTCP is such a massive leap for industries relying on real-time data, we've got to look at the brick wall we've hit. You know those standard text compressors that basically run the internet? Things like ZStandard, LZ4, Brotli? They're amazing for normal data, but you throw a dense 3D point cloud at them and they just choke. We're talking less than 5% compression. That is a total baseline failure when you're dealing with giant spatial data sets.
And honestly, the stuff we've built specifically for spatial data, it's not much better. We're essentially trapped between two incredibly flawed options right now. On one hand, you've got the Draco codec. Sure, it gives you a decent 10-to-1 compression ratio, but the cost is brutal. It absolutely destroys the raw fidelity. The data is permanently degraded. On the other hand, we've got neural codecs. Now, these boast an insane 100-to-1 ratio, but there's a pretty massive catch. They hallucinate data. The neural networks basically just guess, making up fake data points to fill in the blanks. And if you're working with precise, scientific spatial data, guessing is a complete non-starter.
Which brings us to the actual bottleneck holding us all back, the Shannon limit. Traditionally, compression assumes a single entropy model. Basically, it acts like all data behaves in one uniform, predictable way. But that is fundamentally flawed because real-world spatial data is highly multimodal, it's messy, it has distinct, shifting patterns that a single rigid entropy model just cannot wrap its mathematical head around.
And that takes us to Section 2, the core seed hypothesis, or microscopic DNA. Now, what's really interesting here is how much this solution actually feels like biology. Instead of trying to just violently crush a huge data set into a smaller box, SHD CCP actually looks for the mathematical DNA of the shape itself. Just think about the number 12 for a second. The entire protocol revolves around what they call a 12-byte seed. You can think of this seed as a tiny, highly concentrated genetic code for the 3D data. So instead of saving every single individual coordinate of some complex spatial structure, the system computes this microscopic 12-byte seed. And then it pairs it with just a tiny 4-kilobyte residual file to cover any weird structural outliers.
So why is a 12-byte seed such a big deal? Because of this number, 50,000. That incredibly small 12-byte seed, along with that minimal residual file, can flawlessly reconstruct a massive array of 50,000 individual data points. I mean, it's a stunning ratio. It's literally like growing a giant, dense forest of data from a single mathematical acorn.
So the crucial point is that this reconstruction isn't just, a close guess or some blurry approximation. It provides perfect reconstruction accuracy, strictly down to 0.001 millimeter exactness. Put that into perspective for medical imaging. If you're scanning a tumor, you absolutely cannot have a neural network guessing where the margins are. This preserves the exact spatial integrity of the original point cloud, zero hallucination, zero degradation. Moving on to Section 3, math and block classification. Let's look at the structural magic behind how this actually works. So how does it actually sort this messy, multimodal data to find that magic seed in the first place? Well, under the hood, the protocol relies on foundational mathematical constants, stuff that actually appears everywhere in nature. Specifically, we're talking about the golden ratio constants. We have phi at 1.618 and tau at 1.414. These aren't just random digits. They're structural ratios that dictate natural spatial growth. SHD CCP uses them to mathematically define exactly how 3D points relate to each other in physical space. And here is the exact formula driving this compression.
It's the sum of 1 over h multiplied by the sine of phi times h times t. It's beautifully elegant. By integrating those natural constants, the protocol maps out these complex, high-dimensional contexts mathematically, completely avoiding the need to save raw, brute force coordinate data point by point.
But wait, remember that multimodal problem we talked about earlier? To solve that, SHD CCP uses 11 distinct block classification methods. I won't bore you by reading every single technical term here, but just look at the variety. You've got text, binary, numeric, delta, sparse, random. The system dynamically analyzes incoming data and instantly drops it into one of these 11 buckets. It applies the absolute perfect logic to the perfect block, effortlessly bypassing the limits of that old single entropy model.
Let's move to Section 4 and see how this all builds into our ultimate performance comparison, proving SHD CCP's dominance.
This matrix really brings the whole shebang together. Up top, we've got our 1-to-1 raw baseline. Right below that is Z-standard, giving us a measly 1.05-to-1 gain, which is barely worth the processing power. Then there's Draco at 10-to-1, but again, completely destroying fidelity. And Neural at 100-to-1, but just hallucinating data everywhere. Now look at the bottom row. SHD CCP achieves a dynamic ratio between 8 and 50-to-1. But here is the kicker. It keeps 99.99% fidelity, and it does it with a lightning-fast 5-millisecond latency. Think about what that means. Autonomous cars using LiDAR can process their environments instantly. VR headsets can render vast worlds with zero lag. No degraded data, no fake points. Just pure, precise, high-speed spatial compression.
Which leaves us with a truly fascinating question to end on today. If a mere 12-byte seed can flawlessly reconstruct 50,000 spatial points in just 5 milliseconds, what other widely accepted data limits are merely illusions waiting to be broken? We have treated things like the Shannon limit as absolute gospel for decades, but SHD CCP proves that with the right mathematical perspective, those boundaries can just be completely bypassed. So keep questioning those boundaries, keep exploring, and I'll see you on the next explainer.